Dear students, myself Rajesh Nanda, and today's topic is electrostatic potential and potential difference from the line integral of electric field. It is in the chapter 2nd of electrostatic potential and capacitance. In this module, we will discuss the line integral of electric field and electric potential and potential difference. Before proceeding to this, in the class +1, chapter number 6 and 8, the notion of potential energy was introduced. When external force does work on taking a body from one point to another against the force like the spring force or gravitation force, the work done gets stored as a form of potential energy of the body. When external force is removed, the body moves, gaining the kinetic energy and losing equal amount of the potential energy. The sum of the kinetic energy is kinetic energy and potential energy, that sum remain constant. Thus, such type of force, that is called the conservative force. Coulomb's force between the two stationary charge, that is also the conservative in nature. Like the potential energy of the mass in the gravitational field, we can define the electrostatic potential energy of charge in the electrostatic field. Now begin with this topic of electrostatic potential. First we go to the line integral of electric field, work done by the electric field. Negative line integral of electric field that represent the work done by electric field on a unit positive charge in moving it from one point to another in the electric field, represented by WAB, work done between the two point A and B, is given as the negative line integral of electric field. DL, line, integration sign, integral of E represent the electric field between the A and B. For that, we take the 3 coordinate axis, Q positive charge situated at the center of the coordinate axis at O. We take the 2 point A and B. Work is done from the A to B. Take the Q naught positive test charge. Let this Q naught be the test charge taken in place of the unit positive charge, and then force on this Q naught will be equal to Q naught E. Here this A to O, that represent the position vector RA, and this B to O represent the position vector RB. O to A, that is RA, and O to B, that is RB, and from the O to this point P, that is R. The force acting here on this Q naught, that is equal to Q naught E, and it is radially outward. Why outward? Because both are positive charge, Q positive here, and this test charge is also positive. It is radially outward and tend to accelerate the charge. To prevent this acceleration, equal and opposite force, negative Q naught E, has to be applied on the test charge. Then the total work done by the electric field on the test charge in moving from A to B is given as a WAB, integration of small work done. If we take from here the small work between the 2 point, that will be equal to dW, and this whole work done from A to B will be equal to integration of E dl vectors, that give you the final derivation Q naught divided by 4 pi epsilon naught into 1 upon RB minus 1 upon RA. Here you remember something which you have studied earlier, that electric field E, that is given by the 1 upon 4 pi epsilon naught into Q upon R square, and work done, that is equal to integration line integral of electric field between the 2 point A and B. Okay. This equation shows that work done in moving a test charge Q naught from the point A to another point B along the path AB in electric field due to the Q positive, that is situated at the center of the coordinate axis, Q naught charge that depend only upon the position of these points and independent of the actual path. See here, it is depending upon the RA and RB, RA and RB position, and it is only depending on the RA and RB. That means it is independent of the path followed. In between, the path may be different, but in initial and final position, dependency is there. That is, the line integral of electric field is independent of the path, and therefore electric field is a conservative field. Line integral of electric field over a closed path, that is 0. From here you see that a closed path, in the case of closed path, it return to initial position. That means RA or RB will have the same values, and that give you the total work done will be equal to 0. So the line integral of electric field over the closed path is 0. This is another condition satisfied by the conservative force. So that can be represented as, in case of closed path from A to B or B to A, it is represented as a line integral dl of electric field around the closed path is equal to 0. This symbol represents the closed path. This circle represents the closed path. Line integral of only static electric field is independent of the path. However, the line integral of electric field due to moving charge is not independent of the path, because the field varies with the time. Now we come to our topic, that is electric potential. Electric potential is a physical quantity which determines the flow of charges from one body to another. It is physical quantity that determines the degree of electrification of the body. Now the definition of the electric potential. Electric potential at a point in electric field that is defined as work done in moving without acceleration. Work done in moving a unit positive test charge from infinity to that point against the electrostatic force irrespective of the path followed. क्या बोला हमने यहाँ पे बताया कि what is the electric potential, that is defined as work done in moving a unit positive charge from infinity to that point against the electrostatic force irrespective of the path followed. अब यहाँ पे देखो work done, that was represented by WAB, line integral of electric field between A and B, is equal to Q naught divided by 4 pi epsilon naught 1 upon RB minus 1 upon RA. Here we take this, according to the definition, we take this RA is equal to infinity, moving the test charge from infinity to the given point. RA is taken at infinity and RB is taken equal to the R. Then work done here will become, here this value become infinity. We take this Q naught to the work done per unit test charge. Per unit means that it is divided by Q naught. Both equations are divided by the Q naught. Then this become WAB upon Q naught is equal to Q upon 4 pi epsilon naught 1 upon RB minus 1 upon RA. So this W infinity to the point B divided by Q naught, that become equal to Q upon 4 pi epsilon naught R, because 1 upon infinity, that is equal to 0, and this value is the electric potential. So definition is satisfied. Work done in moving a unit positive test charge from infinity to that point against the electrostatic force, irrespective of the path followed. Or potential V is equal to W infinity to the given point B divided by Q naught. And we come to the its unit. SI unit of electric potential, that is volt or joule per coulomb or Newton meter per coulomb. Now the electric potential difference. Electric potential difference between any 2 points in the electric field, that is defined as work done in moving without any acceleration a unit positive test charge from one point to other against the electrostatic force, irrespective of the path followed. Again, we revise this definition. Electric potential difference between any 2 points in the electric field is defined as work done in moving a unit positive test charge from one point to another against electrostatic force, irrespective of the path followed. Unit charge is to be moved from one point to another. W work done, AB, WAB is equal to E into dl between line integral of electric field between the point A and B, that is equal to Q naught divided by 4 pi epsilon naught 1 upon RB minus 1 upon RA. Or when you put this divide this both side by the Q naught, then WAB upon Q naught will become equal to Q upon 4 pi epsilon naught into 1 upon RB minus 1 upon RA. Then multiply these Q upon 4 pi epsilon naught with the 1 upon RB and by the 1 upon RA. Then the equation become WAB upon Q naught will be equal to Q divided by 4 pi epsilon naught into 1 upon RB minus Q upon 4 pi epsilon naught multiplied by 1 upon RA. This will be the potential at the point B and this will be the potential at point A. So this potential difference, it becomes the difference of the potential at B and potential at A. VB minus VA, that is representing the potential, and the difference of the potential, that is given by the change in potential delta V, is equal to WAB divided by Q naught. Electric potential and potential difference, that is a scalar quantity. Electric potential at infinity is 0. If we take this value to the infinity, it will become 0. Electric potential near an isolated positive charge, Q is greater than 0, that is positive. And in case of near the isolated negative charge, Q is less than 0, that is negative. And a CGS unit of electric potential is stat volt or stat volt, that is equal to erg divided by stat coulomb. Now we take some numerical problem. Question is that what potential difference is required to do 100 joule of work to carry a charge of 10 coulomb between 2 points. Understand this question? Here the question is about the potential difference. What potential difference is required to do 100 joule of work? 100 work is to be done is 100 joule to carry a charge of 10 coulomb. तो charge है कितना है 10 coulomb between the 2 points. How to solve this? you know that given values, some given values is that work done, W is that is equal to 100 joule, and second thing given is the charge Q that is equal to 10 coulomb. What is to find out? What potential difference? Now here the work done 100 joule, charge Q is 10 coulomb. Potential difference V will be equal to W by Q. Then divide this 100 by the 10. You will get the answer of 10 volt. Second numerical problem is to calculate the potential difference between 2 points if 1500 joule of work is done to carry a charge of 50 coulomb from one point to another. Here we have to calculate the potential difference. Work done that given is a 1500 joule and charge that is given as a 50 coulomb. Similar to the previous problem, potential difference V is equal to work upon charge. The work will be equal to 1500 divided by 50, that is equal to 30 volt. Example, another example is to calculate the work done to carry a charge of 3 coulomb if potential difference between 2 points is 10 volt. Solution is that we have been given the charge that is 3 coulomb and potential difference between 2 points is 10 volt. Work done is to be calculated. Now we know that V is equal to W upon Q, or W will be equal to Q into V into Q. To multiply this V, we have given the 10 and the Q that is 3. Answer will be 30 joule. Now we come to the another numerical problem from the NCERT book. Calculate the potential at a point P due to the charge of 4 into 10 to the power of minus 7 coulomb located 9 centimeter away. And second part of this question is hence obtain the work done in bringing a charge of 2 into 10 to the power of minus 9 coulomb from infinity to the point P. Does the answer depend upon the path along which the charge is brought? First we come to the first part. Calculate the potential at a point P due to the charge of 4 into 10 to the power of minus 7 coulomb located 9 centimeter away. From this question, you see here the charge given is 4 into 10 to the power of minus 7 coulomb and the distance r that is given is 9 centimeter. The potential V will be equal to 1 upon 4 pi epsilon naught multiplied by Q over R. Here the value of this Q that is given is 4 into 10 to the power of minus 7 coulomb and centimeters. 9 centimeter is to be we have to convert this centimeter into the meter, then it will become 0.09 meter. And the value of this 1 upon 4 pi epsilon naught, that is 9 into 10 to the power of minus 9 Newton meter square per coulomb square. After calculation, the result come out to be equal to 4 multiplied by 10 raising power of 4 volt. Come to the second part. Obtain work done in bringing a charge of 2 into 10 to the power of minus 9 coulomb from infinity to the point P. Now we have to obtain the work. Work is equal to charge into potential. Simple, very simple. Charge given here is 2 into 10 to the power of minus 9 coulomb and the V we have calculated here. Q is 2 into 10 to the power of minus 9 coulomb and V from the calculation, above calculation, it is 4 into 10 to the power of minus 4 volt. Then result will be equal to 8 into 10 to the power of minus 5 joule. The remaining part of this question is that does the answer depend upon the path along which the charge is brought? No. Work does not depend upon the path. It is independent of the path followed. Yes, we have already discussed about it. Any arbitrary infinitesimal path can be resolved into two perpendicular displacement, one along the r and another along the perpendicular to r. The work corresponding to the latter, that will be 0. This whole lecture. First we have discussed the line integral of electric field. Line integral of electric field represent the work done by electric field on a unit positive test charge in moving it from one point to another in the electric field. Then the electric potential. Electric potential at a point in electric field that is defined as work done in moving without acceleration a unit positive charge from infinity to that point against the electrostatic force irrespective of the path followed. Electric potential, that is a physical quantity which will determine the flow of charge from one body to another body, and it is a physical quantity that determines the degree of electrification of a body. Electric potential at a point in the electric field that is defined as work done in moving without acceleration a unit positive charge from infinity to that point against the electrostatic force irrespective of the path followed. Then we have discussed about the electric potential. The electric potential difference. Electric potential difference between any 2 points in the electric field is defined as work done in moving without acceleration a unit positive charge from one point to another against the electrostatic force irrespective of the path followed. Thank you for watching this.